Okay, well, hi everyone. Thanks for coming to our first GCAN GCUS webinar. And yeah, I'll leave the intro to Xinping, but thanks for being here.
Great, thank you. Welcome to our first summer webinar for GCAN. So my name is Xinping Hu. I am working at the University of Texas Marine Science Institute. So previously I was at Texas A&M University Corpus Christi. So here our speaker is Dr. Kanchan Maiti. So Kanchan is a professor and the chair of the Department of Oceanography and Coastal Sciences at the Louisiana State University. He holds the Shell Professorship in Oceanography and Wetland Studies. So Kanchan earned his PhD degree from University of South Carolina, and he conducted postdoc research in what's called Oceanographic Institution. So Kanchan has done a lot of work, and he specialized in marine geochemistry, and in recent years, he's been focusing on the fate and transport of the carbon across land, estuary, and ocean continuum. And of course, his fieldwork has covered many areas. A lot of it is in the Gulf of Mexico, and he has also done work in Turkey, Antarctica, that's the other end of the earth. So today, he's going to be talking about the benthic-pelagic interactions in the Northern Gulf. So without further ado, so Kanchan, here you go, please. Thank you.
Thanks, Xinping. Thank you all for coming to this webinar. I'm happy to talk about one of my favorite subjects here, the coupling between the benthic and pelagic environment, especially in our part of the Gulf of Mexico, where we have a shallow shelf. And so in this talk, what I'm going to talk about is how all the storm events kind of amplify these benthic-pelagic coupling. So this work was done a few years back, and there's a photo showing all the students who helped with this work. And I'm glad to say almost all of them graduated. Some of them are actually already faculties. So that means I'm getting older and older. But this paper never got published because this work was funded by NSF, kind of a rapid proposal. And you know what happens with rapid proposal. You do not have some defined person working on it. So I'm still working on it over this summer. And that's why I thought I'll put this up today. And hopefully I can get some good feedback from you all. So we're going to go back to Hurricane Harvey. That was right here. And that was the year in 2017. We have Harvey hitting Texas. We're all familiar with that. Then we have what we are not familiar with was in that year, we have few more hurricanes that also came through. And there was one called Hurricane Nate, which was a category 1 that actually hit Louisiana. And then there was Irma, which was on the other side. For this talk, we're kind of focusing on this area of the Gulf along the Texas-Louisiana border in this shelf area. And the idea of this work was what happens to the sediment after these storms? Where are they redeposited? Where they moved from? Do we get a lot of new sediments? And the most important part, which I think was what the main focus was, is how does this sediment redistribution, resuspension impact the water column biogeochemistry? And in turn, how does it impact the carbonate chemistry and carbon cycle? That was kind of like our ultimate goal. So obviously, if we look at the satellite data, it's no surprise that if we look at the suspended load between August when Hurricane Harvey happened all the way through October, we can see there was definitely a lot of new and resuspended sediment that was coming up. In August, it was high after Hurricane Harvey, then it started going down, and then it went up back in October when we had another storm hitting this area. And so we were actually fortunate. We were able to mobilize, get funding, mobilize our crews within 4 weeks of Harvey. So we were out there in less than a month. And even when we went out there, we found the suspended solid, the TSS, was actually quite high across the shelf. These are all the stations that samples were collected from. And it still showed that the remnant of Hurricane Harvey was still there, even after almost 4 weeks. So first part of this talk is to try to understand what happens in the sedimentary phase in the seafloor. So for that, it's kind of tricky to look at sediments and explain whether or understand whether they are newly deposited or old sediments. So we have to rely on some tracers. So what we did was we used this beryllium-7 and thorium-234 tracers to look at the sediment that were redistributed after these Hurricane Harvey. And the idea is beryllium-7 usually comes with wet deposition. Majority of it comes with wet deposition. So that means after a storm event, there's a lot of beryllium in the water column. And because beryllium is sticky, it sticks to particle, it will sink to the bottom along with the particles. So that kind of tells us an idea about the newer sediments that are getting deposited. Thorium, on the flip side, is not from atmosphere. It's already present in the water column. Thorium-234 is also sticky, but in this case, what can happen is if the sediments are resuspended, they'll go into the water column, scavenge the thorium in that water column, and sink back. So either way, both these isotopes, because they have such short half-life of 50 days and 24 days, if we find a lot of beryllium or a lot of thorium or both, we can expect these sediments to be deposited fairly recently, within the past month or two. But because these two isotopes have very different pathway, beryllium-7 often kind of points towards newer sediment deposit, whereas thorium can actually point to both newer deposition and recycled or redeposited sediments. They do not discriminate. So that gives us a little bit more control on explaining the sediment deposition in the shelf. So with that, we went out and collected samples from 21 stations along the path. This is the hurricane path for Harvey. This is the hurricane Nate on either side. So we have August and October. And we collected samples from across this shelf all the way up to 40-50 meter isoband. And I'm going to focus on these three transect right here: K transect closest to the Hurricane Harvey, F somewhere in the middle, and C station, which was closer to the Nate. And I'm going to go through this fairly quickly just to show how the sediment is very different from starting from this side of the shelf, the Texas side, to the Louisiana side. As we might expect, we expect more sandy part material here and more muddy on this side, on the Mississippi, Louisiana side. And if we look at these sediments, the way this is, we have kind of a top 12 centimeter worth of sediment shown here. I'm looking at the middle graph here, which has depth on x-axis and grain size on, depth on y-axis, grain size on x-axis. And on the top panel, we kind of integrated the grain size distribution into three classes: clay, silt, and sand. And on the bottom panel, we have the depth and beryllium-7 presence in the sediment. And what we can see in this third panel at the bottom is there is beryllium all the way up to 9 centimeter, even up to 11 centimeter. That is probably the deepest we found beryllium-7. And the sediment structure kind of shows these are all kind of, they do not have any bioturbation in them. Seems like massive rapid deposition, suggesting these were indeed deposited after the storm. And what this is telling us is that at a minimum, top 8 centimeter of the sediment was either newly deposited or a combination of new deposit and resuspended material that got settled back. Either way, that's a lot of sediment mobilization we're talking about. And if we look at the top panel here, which shows the cumulative grain size, we can see most of the material falls in that silt category for this K transect, which is close to Texas. And if we now move on towards the east to the F transect, which is somewhere along the Texas-Louisiana border, we kind of see that now it is moving a little bit more sandier. The top yellow is sand, but we still see beryllium-7 deposition, not as deep as it was close to the Hurricane Harvey path, but still about 5 centimeter deposition of sediments right there. And these sections of the core are X-rays. You can see they're massive layers. There's barely any bioturbation in them, suggesting they're deposited very rapidly. And then my favorite station, C6, which is where we always go every time I'm going out in the Gulf. And here again, we see something different. Now we're not looking at sandier material, which makes sense because we're in the influence of Mississippi River, but a lot of silt. But irrespective of that, we still see a lot of coarse material, and we also see a lot of beryllium-7 penetration all the way up to 9 centimeter. And this is fairly interesting because the first two panels, these were in September and October, and the last one is actually right up 2 days after Hurricane Nate, because we were actually there. And we can see right after the hurricane, it almost got 11 centimeter sediment that were redeposited, showing that even if we are farther from the storm, we can get a lot of material that are resuspended or new material that are coming in and that are getting deposited. So what does that mean? So we can see the time evolution and the spatial evolution going from these three transects that I showed you. These first two are more like temporal scale, spatial scale, and the last one is more like temporal scale, starting from September to October, where we see a lot of sediment that were remineralized and getting deposited, because this station is only at 20-meter isobath. And so what this tells us is that irrespective of whether we can answer how much of this new sediment is new or how much is resuspended and redeposited, there was a lot of remobilization of sediment. So put that in perspective. So we have a map here which shows the bubble plot. The size of the bubble tells us how much was the sediment that was redeposited or newly deposited after a hurricane. And we can see that it varied anywhere from 4 to 10 centimeter across this Texas Louisiana shelf. And that translates to about 0.5 mil to 6 millimeter of sedimentation per day. And just to put things in perspective, the only data I found from this side is Carlin et al. 2014, and they found the average sedimentation rate for the year at the start is about 1 to 4 millimeters. So we are seeing about the same range of sediment mobilization from one storm event that usually would otherwise happen throughout the year. And same study, same case for Louisiana shelf. We're seeing about 3 to 10 millimeter under usual circumstances, but here we are seeing an orders of magnitude higher sediment that were redistributed and redeposited. So if we start looking at this data in terms of the isotopes that we use to figure this out, we can do an integrative inventory of this isotope, because what that tells is the total amount of beryllium-7 that was deposited. So more is that number, most likely more is the sediment that was deposited. So if you look at it from that perspective, we can still see that some of the highest deposition are taking within that 20-30 meter isobath, whereas further out the sediment deposition goes down. If we look in terms of thorium inventory, remember that is basically stripping out the water from thorium, whereas beryllium is coming from external source. In thorium, we see similar case also, but not quite the same as beryllium. So what this is indicating is we can use these two ratio in their inventory to understand whether or what fraction of the sediment is new versus what fraction is redeposited. So usually higher thorium beryllium ratio would indicate predominantly redeposited sediment. And we can see those happen, not surprisingly, further offshore, where we still have resuspension from the wind event and the currents and the waves, but not necessarily enough sediment, new sediment coming in and getting deposited. Whereas the ones closer on to the shore in the shallower isobath probably are getting new sediments coming off the coastline that are getting deposited along with sediments that were resuspended. So if you start putting all those things in perspective, so here is the path again, here is the shelf we are talking about. And if I just do a very modest back of the envelope calculation, let's say on average we have 4 centimeter of sediments that were redeposited, which is far less than what we saw. We saw in the range of 12 to 4 centimeter. So even if I go with the lower limit and then we scale it up for the entire area of that 50-meter isobath shelf, which is roughly 80,000 kilometers square, we can do a back of the envelope calculation using the density to come up to about 7 times 10 to the power 9 metric ton of sediment that was mobilized, combination of new and resuspended sediments that were deposited or redeposited across this shelf. And just to put that in perspective, that's one hurricane. doing the work of the entire Mississippi Atchafalaya River system for a year and way more. So this tells us the scale at which the sediments were resuspended and redeposited after this hurricane event, more than what Mississippi Atchafalaya River brings in. And what does that mean? So if you have that much of sediment that got ejected into the water column, it's not just sediment, right? So we can now start thinking about the carbon in that sediment. So we know roughly these sediments have about 0.5% of TOC in them. So if we start using that number, multiply it with the total sediment resuspension and redeposition that happened, we come to about 3.6 times 10 to the 7 metric ton of particulate carbon that was in the water column due to this hurricane. So what happens to that organic carbon that got resuspended, that got remobilized, that got redeposited during and after this storm event? So the next part of the story is what is the impact of this very rapid ejection of organic matter into the overlying water column, and that's the coupling and that we can look into. So we had idea to put in benthic landers, the benthic lander system that I showed in the first figure. I'll show you the last figure where you can see that it is actually breaking up due to the rough seas. So unfortunately, the lander didn't work because all the chambers were shattered, but we were at least able to do core incubation, which was our backup plan in case the lander breaks, because we kind of knew that can happen. So these are all from sediment core incubation done at these stations. A lot of it was done by Loretta, who was with us. So thanks for the data. But what we can see here is the DIC fluxes over time. And these are for the different stations, as the D5, and then I have only one station, but we have other station data. But what we can see here is during July, prior to the Hurricane Harvey, when we had a cruise going out right during the hypoxia, the DIC fluxes, which is an indicator of organic carbon remineralization happening in the sediment and coming out as dissolved in organic carbon, we can see that DIC flux was relatively low in July. Right after Hurricane Harvey, when we had all the sediment resuspension and the remineralization rate in the sediment went up by about factor of 3 at the same station. Then again, when we went out during Hurricane Harvey, remember this is October, so it's kind of getting late in the season, we had even higher DIC flux of 21 millimole per meter square. So what this tells us that one of the response that happened due to this rapid sediment mobilization was increased organic carbon respiration in the sediment by factor of 3 to 5 over what we see during July. So what about the water column above these sediments? So these are very elementary work done to look at primary productivity and respiration using light dark bottles that was done on the cruise. And what it is showing us is in July, for all these stations, all these dots here are kind of showing the stations where samples were collected from. And we also had a bottom sensor at C6 that I'll show data from in the next slide. But overall, if we look at July shelf-wide, primary productivity was higher than respiration in the water column. After hurricane, the ratio of P to R is less than 1, meaning respiration is more than photosynthesis, and the same is true for October. So not only did we see higher respiration rate in the sediment, we're also seeing higher respiration rate in the water column above it, which makes sense because we had all the sediment that got ejected into the water column, made the water more turbid, so obviously photosynthesis will go down. But at the same time, we also ejected a lot of organic carbon, which are going to be respired, so your respiration rate went up. So literally, we had much higher heterotrophy due after these hurricane events. So what does that mean in context of the oxygen? So if we think of it, both these processes, this DIC increase in DIC fluxes means increase in oxygen consumption, because a lot of this is driven by aerobic respiration. In fact, majority of it. Same in the water column. More respiration means more oxygen consumption. But we usually think of hypoxia that happens in the right here in this area as a time when the oxygen is really low. So whenever there is a storm, the usual paradigm is we should break that stratification, we mix the water, it becomes oxygenated, so you have less hypoxia. But what this is showing is that you break up the water column, you add oxygen into it, but we also inject a lot of organic matter, and you increase your oxygen consumption. So yes, you can break the hypoxia. So this is a kind of a time series graph which shows both oxygen data at the bottom and model data shown in this orange. What we see here, and the shaded area of 2 is your hypoxia range. What we see here is that, sure, we get hypoxia, then after the passage of storm, oxygen goes up. But what is surprising, what we found interesting is oxygen also rapidly goes down. So which means this hypoxia or this low oxygen bottom water is actually quite resilient than what we would think. And the main reason for that is, although the water gets oxygenated, because we're increasing our oxygen consumption rate in both the water column and the sediment, we are going back to those hypoxic conditions fairly quickly. So there is that recovery of hypoxia that is happening much more rapid than what we thought it would be, and as a result of this enhanced respiration. And we kind of see the same thing in this nicer figure. We see this recurrence of hypoxia that gets broken up, oxygenated, but very quickly goes back to hypoxic condition. Same after this, even after the storm in October, we can see a hypoxia forming. So what else is happening beyond oxygen and DIC production? Of course, when you have more CO2 production through respiration, we expect more surface CO2, and that is exactly what we see. So we have this transect of PCO2, surface PCO2 across this shelf. This is data courtesy from Weijun-Kai's group, and we can, and because we're right out there during Hurricane Nate, we literally had to get away from the hurricane and come back and sample. We had this awesome opportunity to look at the CO2 in the surface water pre and post storm. We are talking about 2 days, 2 or 3 days apart between these two CO2 graphs that we see here. So before Nate, shown here in green, after Nate, shown here in yellow, and we can see there's almost 100 ppm jump in CO2 concentration, which is not surprising given the higher consumption rate and respiration rate. And a reason, and that of course translate to a drop in pH, and you can see almost 0.1 unit drop in pH, which is almost 100 years worth of ocean acidification, I think, and that is happening after this storm. But what we really don't know is what is the recovery period? How long is this sustained? That we unfortunately didn't have that kind of time or sampling effort to look into this, but I think that is a question that definitely needs answering going forward. Is like, so after all the storm events, we have high oxygen consumption, enhanced CO2 production, drop in pH, but how long does it last? How long is the recovery period? So, and ways to do that would be maybe just look at the surface CO2 at the buoys, or other ways like gliders that can help us understand what is this recovery period for this carbonate system in this shelf after these perturbations happen. And here is another example showing some historical data from 2006 that I'm sure you're familiar with here. And then we have the 2007 data again showing much higher PCO2 at the surface compared to regular season. And so what that aspect does need further studies to understand how much increase in CO2 source does the coastal ocean contribute to after the passage of these storms, and how long does it take for it to come to equilibrium again. So that's pretty much what I wanted to talk about. So we can kind of wrap it up by saying that we have huge amount of sediment that got mobilized along the Texas Louisiana shelf from just one single storm that happened much west of Louisiana, but we can still see the impact on the Louisiana side. Then also the heterotrophy was increased in the water column, and same with the sediment. Sediment organic respiration rate went up, and this combination resulted in higher CO2 concentration in the water column, higher CO2 flux into the atmosphere, and drop in pH that came along with it. And surprising result is the self-hypoxia is much more resilient than we thought it would be to these storms, because they seem to go back to hypoxic condition very quickly for this enhanced oxygen consumption that happens. And what I think we don't know is how long does it take for the system to return to pre-storm conditions. And I think that is the key to really get a more of a mass balance understanding of how much contribution is happening and how the entire system is moving. With that, I would like to acknowledge both Wei-Chun Kai and John Lerater for their data, and also Okil, who is now a faculty at Southern Miss, and Byron. Both of them really helped me with this cruise, and all the crew who gladly helped us through this. You can see that weather was nasty, and this is the slide I referred to earlier. This is the slide where I actually watch my lander shattering in front of my eyes and hoping I don't slide into the water. With that, I will stop, and I'll be happy to take questions.
Awesome. That was great. I feel like this talk is really big now with all of the big storms that are coming, and we can predict with models how all of this more coastal region is going to change with the changing climate and stuff. So that was a great talk. And for all of you guys online, you should have a question panel on your screen. So that would be a great way, place to put in some questions to ask our speaker. There isn't a way to unmute, but if you want to drop a question, that is how you should do it. But I can start us off. For your map, you showed a hurricane, I think it was Irma, also in that same time. How do you, or do you know the continental margin and shelf and the slope of that region, and seeing kind of what they would have seen in their coastal zone compared to their northern Gulf?
What to do, unmute, forget to unmute every week once, right? I do not remember specifically about Irma, but we did go there after Ian and collected sample, which was recently. But one interesting thing, and that was a really cool paper that I came across, it is very different on that side of the Florida side, is because Florida is very different from Louisiana and to some extent Texas. They are actually nutrient limited, right? They do not have as much phosphorus. And in fact, these storms can bring in phosphorus, and they can actually lead to better response to the vegetation in the marshes. And there is this really cool paper showing mangrove forest actually growing more after some of the storm events, even though they got disseminated by the storm, which is, I thought, was a really counterintuitive response to a storm and very different from our side of the Gulf.
Yeah, that makes sense. Thank you. Okay.
Well, can I have a question? Yeah, so Kanchan, a very interesting talk. Actually, this is the first time hearing you put this together, including sediments, water column. So my question is, with this type of the scale of sediment remobilization, resuspension, and deposition, just curious your comment on the benthic-pelagics, because if the sediments are resuspended on such a large scale, and then if people, because EPA and I think also some Louisiana scientists back in the years have measured a bunch of benthic respiration rates, because I never really compared the timing of those measurements with the occurrence of the storms. How would you comment on the rates? Can those rates be used as input, for example, in Kanchan's model, in terms of calculating the development hypoxia or biogeochemical cycles?
Yeah, I mean, Xingping, that's something, that's a head scratcher. In fact, if you look at the data, depending on which data you put together, you can almost see a positive relation of oxygen consumption versus oxygen concentration, or a negative. Depends on which data set you start putting together. You can put some data and it will give you a positive correlation, and some of them shows a negative correlation. And I think a lot of it has to do with, as you suggested, is the timing. It's like what happened prior to it, what kind of sediment we're looking at, and that can really impact these numbers. And I don't know how to handle that in a model, and which data to use and which not to use. But that is definitely something that we need to look at. And actually, only recently we got a new paper that came out in Frontiers, which showed also that the benthic community can also impact even in the hypoxia zone, which is another layer of complication, because you always think of the hypoxia zone to have not much benthic community, but they are responsible for part of their oxygen consumption too, especially nematodes. So that is another layer that can impact our oxygen consumption rates, and that is almost not there after a storm because it pretty much smothered everything with that massive deposition. So that's another layer that also needs to be accounted for if we try to use calibrate these models with oxygen data.
Right. So my other question is I remember we used to talk about it as well. So with this storm and the after storm, the hypoxia can restore fairly quickly. Also, given the time scale of the two gas exchange rates, oxygen got replenished very quickly,
Yeah.
but CO2 degassing is a lot slower.
Yeah.
You expect to see, after this type of storm occurrence, there may be more of this acidification effect.
Yeah. I think what guys that I think it's this Nature paper. I think he makes that point, or this that I agree. I think because you will keep accumulating, because you got an system which has more oxygen in it, and your CO2 is staying longer, so you'll keep on adding, piling on. And I agree. I think it will lead to a cumulative effect on the CO2 side.
Right. It'd be interesting to have this, because you guys are close. Just maybe observe after another. I hope there's no storm coming your way, but then still, if there's any in that area, stay in shore, offshore maybe. There may be observations. So the data that support the hypothesis.
Yeah, that'll be fun. Yeah. If I can find somebody to go with me. Not everybody was happy after the cruise.
Yeah, it is rough after the storm.
Yeah.
All right, well, we also have some questions in the chat. The first one is, what volume of sediment sample is required for the isotope analysis?
Okay, so it's really about, so we can do it in many different detectors. I have detectors which can start from taking about, it can do with 2 gram to 20 gram of dry sediment, based on which detector I'm using. Obviously, the 2 gram will take a longer time to get a measurement and will have less certainty. And the more it is, the better is the error.
Okay,
but anywhere between 2 to 20 gram, we can do it. But the key is the sediments needs to be measured very quickly, because these are very short-lived isotope. We're talking about 24 to 50 days half-life. So if the sample is with us, after 30 days, we'll already lost half of it.
Yeah, that makes sense. All right, and then the next one asks, on your maps, are the hurricane paths the eye of the storm? And then any idea how far from the eye of the storm the hurricane, the tropical storm force winds may have extended?
Yes, and that's a really great question. Yeah, that is, we actually have some OF data from C6, and obviously the fetch wasn't as bad obviously as this area, but it definitely was felt here. And I think the other thing we have to keep in mind is not about the wave and the current dimension that is changing in the shelf, it's also the impact that it is having on all this runoff, both from streams and land boundary runoff, that is also bringing a lot of water and sediment to the system that gets redistributed. So it's both the physics on the ocean side and the hydrology on the land side that will have a cumulative effect on these sediments. Does that answer?
I think so. Yes. If you asked that question and you wanted to ask a follow-up, just put it back in the chat. We'll see. And any other questions, feel free to put them in as well. Okay, answered the question. All right, well, I think those are all of our questions. Well, thanks for your time and a great talk, and thanks to all of the participants for coming to the first GCAN webinar.
Thank you for inviting me. That's awesome.
Yeah.
Thank you.
Thank you. Bye, everybody.